Good morning, good afternoon, and good evening, everyone. Welcome to today's Advanced Nanotechnologies for Water Purification webinar, the second of our webinar series organized and hosted by the IWA Nano and Water Specialty Group. Today, I have the honor to tell you a little bit about the webinar series and introduce two excellent speakers for today's webinar. So this just some housekeeping information. This webinar will be recorded and made available on demand on the IWA Connect Plus platform. So if you wanted to review and rehear the webinar, you can go to the site afterwards. And everything that the speakers will present has already resolved or have received all the copyright permissions, so that information can be shared with you all. And also a disclaimer: the opinions, hypotheses, conclusions, or recommendations contained in the presentations and other materials are the responsibility of the speakers, and these do not necessarily reflect the opinion of IWA. When you are in the webinar, if you have questions, please type your questions using the Q&A box. So if you click the Q&A box, type your questions there, the moderator will collect these questions, will answer all the questions at the end of the webinar after both presentations have finished. And if you have other things you wanted to discuss, either with the speaker, the moderator, or other audiences, you can use the chat box. So this is today's agenda. After the welcome introduction, we will have the first presentation by Professor Yanbiao Liu from the Dalian University of Technology in China. The title of his presentation is Electrified Membranes for Environmental Applications. Our second speaker, Dr. Xin Xie from Georgia Institute of Technology, will then speak about nano-enabled LEEFT for water disinfection. That will be followed by a Q&A panel discussion moderated by Professor Paul Chen. And the webinar will also be closed by Professor Paul Chen from National University of Singapore. So a little bit of history about our specialty group. And the IWA Nano and Water Specialty Group is set up to provide an active forum for professionals and researchers interested in the application and implication of nanotechnology. In the past, we had a very strong focus on the environmental fate and transport and risk of nanomaterials, and it was an excellent platform for exchanging knowledge and research on these topic areas. Now we're more focused on promoting the development and advancement of nanotechnology from the lab scale to technological scale for water and wastewater applications, including the water and energy nexus, but with minimized risks, and to extend knowledge to other fields and applications, as I mentioned, including energy applications. So we are trying to grow our specialty group, and so we welcome anyone who may be interested in these topic areas to join our specialty group. Some brief introduction about today's speaker. Again, I have the great honor to introduce two excellent speakers for today's webinar. Our first speaker will be Professor Yanbiao Liu from Dalian University of Technology. Professor Yanbiao Liu received his PhD degree in environmental science from Shanghai Jiao Tong University in China. And then he did his postdoctoral training at National University of Singapore at the Environmental Research Institute. He is currently a professor at Dalian University of Technology, and his research focuses on environmental nanotechnology, with a strong interest in development of electroactive filters for environmental applications. He is a very productive researcher, has published over 150 research articles, and with a very high citation, above 10,000. Our next speaker, second speaker, is Dr. Xin Xie. Dr. Xie is the Carlton S. Wilder Associate Professor in the School of Civil and Environmental Engineering at Georgia Institute of Technology. He received his bachelor and master's degree in environmental engineering from Tsinghua University, and then went to study at Stanford University, where he received a master's degree in material science engineering and a PhD degree in civil and environmental engineering. His postdoctoral training was at Caltech, California Institute of Technology. Dr. Xie's current research focuses on the applications of novel materials for sustainable and reliable water and energy. He has worked on many projects related to water treatment reuse, microbial detection, and inactivation, quantification, energy and resource recovery, storage, and so on. He's another excellent, very productive researcher, has published a very high number of articles in top journals with extremely high citation of over 10,000. So with that, we'll move on to our first presentation. I'm very pleased to give the floor to Professor Yanbiao Liu for his presentation.
Thank you, Professor Li, for your kind introduction. And also, I would like to express my gratitude to Professor Paul Chen for his kind invitation. It's my great pleasure to give a talk here. And today, the title of my talk is Electrified Membranes for Environmental Applications. My name is Yanbiao Liu from Dalian University of Technology. So today, my talk was divided into 4 parts. Firstly, I'm going to briefly introduce the background of my research, and also I would like to give some examples on the combination of membrane with electrooxidation and electroreduction. And finally, I will conclude my talk. So for the background part, currently, there is a pressing need for water all over the world. Based on statistics, the global water and wastewater treatment market size is expected to hit about 500 billion by 2030. Particularly in China, advanced water treatment technologies are highly demanded to fulfill the dual carbon goals, that is, to achieve peak carbon by 2030 and carbon neutrality by 2060. There are 2 major types of water treatment technologies. First is based on separation. They can separate pollutants with water, such as adsorption and membrane filtration. The other is based on transformations. They can oxidize pollutants in the water, such as activity sludge and AOPs. However, both have limitations, such as membrane fogging and poor reaction kinetics. It would be highly desirable to combine the merits of both technologies. That is the motivation for us to carry out research on the electrified membrane technologies. This technology was firstly proposed by Dr. Chad Wistis at Harvard. It combines membrane separation and electrochemistry. Here are some pictures of the device. This is a hybrid of physical adsorption and chemical oxidation. By using the flow-through operation, the mass transport can be greatly enhanced by convection. And once we apply electric field, it can decompose organic molecules, can deactivate bacteria or pathogens, and also catalyze some reactions, like to catalyze the production of hydrogen peroxide, or other chemicals. Such hybrid design features several advantages, like enhanced mass transport, mitigated membrane fogging, and also have multiple functions. Since electrochemistry have different functions, we can also incorporate these electrochemical processes into the membrane process, such as we can incorporate oxidation, reduction, electroosmosis, electrosorption, and other processes into the membrane filtration process. We have currently developed several electrified membrane materials like carbon nanotubes, CNT, graphene, MagSeed, MOF, copper or silver nanowires, and they all share some similar attributes like electrically conductive, mechanically robust, have large surface area, and also solution processable. Next part, I'm going to briefly introduce some examples on the combination of membrane with electro-oxidation. So we can achieve rapid degradation of organic molecules due to the synergistic effects between flow field and electric field. We have treated several kinds of organic molecules like phenols, dyes, antibiotics. The reaction kinetics was about 1 order of magnitude higher compared with conventional batch electrochemistry. And right now we are working on upscaling of the experimental setup for industrial applications. We can also achieve selective oxidation of electron-rich compounds by inducing the production of a singlet oxygen rather than hydroxy radicals, which is non-selective. Once we load some Fenton catalysts onto the CNT side walls, hydroxy radicals will be the dominant draws in the system. This is in accordance with conventional Fenton chemistry. However, once we load the Fenton catalysts into the CNT chambers just to confine them, singlet oxygen will become the dominant draws instead. And we have developed several nano-confined Fenton catalysts, such as iron oxide, titanium dioxide, manganese oxide, and others. Another interesting finding is that the presence of a silicate in the system could greatly boost the yield of singlet oxygen, thus lead to enhanced organic degradation kinetics once involved with silicate. Another example is about the valence state regulation of some heavy metal ions. For example, antimony is typical pollutants in the textile wastewater, which is usually with a charge of 3 plus, and this antimony 3 is highly toxic, also neutrally charged. However, another state of antimony is antimony 5, which is 10 times less toxic than antimony 3. So we just try to transform antimony 3 to a less toxic antimony 5 by oxidation. And the applied electric field assumed 3 roles in this process. Firstly is to oxidize highly toxic antimony 3 to antimony 5. And the second is to accelerate the mass transport of negatively charged antimony 5 by electrostatic attraction, since we exert positive charge on the membrane. And the third is to dissolve the antimony 5 by exerting an opposite charge. And also we can load some nanoparticles like titanium dioxide to absorb this antimony 5. We give it a name called valence state regulation strategy, and we further applied this strategy to the treatment of other similar pollutants, like we can oxidize arsenic 3 to arsenic 5 and to absorb them. We can also reduce chromium 6 to chromium 3 and also to absorb them with some adsorbents like PANI, penny. Also, for persulfate-based AOPs, which is a hot topic in environmental field, we need to add persulfate into the system. However, in some industrial wastewaters, it also contains high concentrations of sulfate. So, whether we can make use of this sulfate to produce persulfate. With this aim, we have designed a sequential electrochemistry system. We try to oxidize sulfate into persulfate at the anode and then further decompose this persulfate into sulfate radicals at the cathode. And these sulfate radicals will react with pollutants in the system, and after reaction, these sulfate radicals will convert back to sulfate again. So it achieves sulfate circulation in the system, but accompanied with the removal of organics in the system. So we have determined the generation of persulfate at the cathode, as you can see the signal here, and also we can also determine the production of sulfate radicals at the cathode using EPR, some radical scavenging test, and all these are in well accordance with our hypothesis. The next part, I'm going to give some example on the combination of a membrane with electroreduction. So the first example is about through selective removal of some nitrogenous pollutants. Since copper have high affinity to nitrogen moiety of organic molecules, so in this work, we try to make use of this point to achieve selective abatement of nitrogenous pollutants. we fabricate copper nanowire networks to serve as like both cathode and also as a filtration medium. Once in contact with nitrogen molecule such as amino, the copper nitrogen bond will be formed in situ. And such copper nitrogen bond, they tend to obtain electrons from PMS molecules to achieve PMS oxidation. Meanwhile, protons in the system, they tend to convert into atomic hydrogen under electric field on the copper side. Such atomic hydrogen, they can reduce PMS once in contact. So such design system, a coupled copper nitrogen bond mediated oxidation and also atomic hydrogen mediated PMS reduction so that PMS can be decomposed very effectively. And another advantage of this technology is highly selective to only nitrogenous pollutants. We have tried about 15 compounds. Only those have nitrogen size can be effectively degraded with very high efficiency and high stability. Also, another example is about the single atom catalyst. Since single atom catalysts are very ideal for catalytic applications due to the almost 100% atomic efficiency, so we have developed a single atom catalyst based flow-through electrofusion system using different single atom catalysts such as iron, copper, or cobalt, and they all demonstrated enhanced oxidative capabilities. For example, in the iron single atom catalyst system, the dominant reactive oxygen species is sulfate radicals. However, in the iron nanoparticle-based system, the only difference is the size of the particles. The dominant reactive oxygen species become hydroxy radicals. So we can change the reactive oxygen species by changing the size of the nanoparticles, the catalyst. And also we can synthesize ammonia from nitride by using electrified membrane technology. We also found that the ammonia yield and the Faradic efficiency of the system was highly size dependent, coordination dependent, and also wettability dependent. For example, by using different catalyst size, just changing the size of the iron catalyst. We compared iron single atoms and also iron nanoparticles. The ammonia selectivity and also Faradic efficiency was quite different. As you can see, the iron single atom catalyst was outperformed with the iron nanoparticles in this part. Also, we can recover some resource from water. For example, we can recover phosphorus from water by using calcium carbonate to modify the CNT filter. Under electric field, the produced protons they will react with calcium carbonate to release calcium ions. And this calcium cation will combine with phosphate to form calcium phosphate precipitate at the cathode surface. And after reaction, we can recover these precipitate to recover them. And also another example is to recover gold from water. To do this, we just only need to load some MOS2 particles onto the CNT filter. And those sulfur molecule will have high affinity to gold ions, and which will further reduce by the MO size to reduce to gold zero. And we call this technology high-tech alchemy since it can achieve very effective recovery of gold from water and also have very high selectivity as well. Here are some cover papers we have published in recent 3 years, including some leading journals in environmental field like EST engineering, EST water, and some others. So finally, I'm going to conclude my talk. Compared with AOPs, our electrified membrane has the following advantages. In this technology, we don't need to involve hazardous chemicals, and both the operation cost and the device cost are very limited. And since it can combine two operational units into only one part, so it can also save the land usage. We believe this technology is suitable for some point use application. Also, we can achieve the selective removal of some pollutants from even complex water metrics as well. So at last, I'm going to thank the financial support from NSFC of China, and also some collaborators like Dr. Chadwick, Dr. Shi Jieyu, Dr. Xiao Guangdun, and others, and also thank my students for their hard work. Thank you. Thank you.
Thank you, Professor Liu. And for those who have questions, we will address after the talk. And next speaker is Professor Xie. Professor Xie, please start. Thank you.
Okay, thanks, Dr. Chen. Let me see. Okay, yeah, so hello everyone. So it's really my great pleasure to be here and then have this great opportunity to share what we have been working on in the past few years on this specific new technology for water disinfection. I assume most of you are familiar with water disinfection, so I will just go ahead and introduce what is LEEFT. We call it LEEFT here. So to explain what's LEEFT, I need to explain what's the electric field treatment first. That's the EFT. So basically, this is a schematic showing the parallel electrodes. So you have a positive electrode, negative electrode, and then orange lines here indicates the direction and the strength of electric field. And then we have the cells here, so exposed to this external electric field. So basically, because of the external electric field, the charged ions in the media will basically, the positive ions will move towards the negative side, and the negative charged ions will move towards the positive side. And the movement of these ions will actually squeeze the cell membrane and then generate this, we call it transmembrane potential. And then this transmembrane potential is proportional to the strength of the external electric field. So at a certain stage, basically this external electric field will be able to generate pores on the cell membrane. And then we call this process electroporation. So this electroporation process can actually kill the microorganisms. And then you just need to achieve significant high enough electric field strength. So theoretically, we can use that to kill microorganisms. But the challenge is that typically we need to apply the electric field that's very strong, and then usually we have to apply several kilovolts of voltage with a small gap distance between the electrodes. So to address this challenge, we want to apply it for large-scale water disinfection. We try to develop this kind of locally enhanced electric field treatment. So that's the LEEFT here. So basically, the idea is that instead of generating a uniform electric field using two parallel electrodes, we basically want to locally enhance the electric field. So in that case, we don't need to apply a very high voltage. We just need to apply a very small voltage, but at certain locations in the treatment chamber, we have a very strong electric field that's strong enough to kill the microorganisms. So there's two strategies to allow us to realize this locally enhanced electric field strength. So at a macro scale, so it's basically macro scale or micro scale. At a macro scale, basically relies on the design of the electrode, design of the system. So for example, we can have this kind of coaxial design. Basically, we have a center electrode, we have an outer electrode. So according to the physics, the electric field strength near the center electrode can be much stronger than the outer electrode. And then another scale is a micro scale. Basically, we can just modify the surface with this kind of a nano tip structures. And it really depends on the aspect ratio of these tips. The electric field strength near the tips can be several orders of magnitude stronger than the background electric field strength. So basically, both these two strategies, the idea is that we want to locally enhance the electric field strength. So, and then the certain locations, the electric field strength is very strong. So we can basically try to transfer these microorganisms to these regions so they can be inactivated. Combining these two strategies, we have developed we call it tubular-shaped coaxial electrode configuration of the LEEFT device. So as you can see here, basically we have a center electrode and then we have outer electrode. And then for the center electrode, we further modify the surface with these kind of tip structures. Okay, so here's a simulation showing that the electric field strength near the center electrode, especially at the tips of these nanostructures, can be significantly enhanced. And then here shows the image of the first prototype developed in our lab. So basically, it's just a small scale, just a few centimeters long, and then about 1 centimeter in terms of diameter of the treatment chamber. And then for the outer electrode, it's basically just a copper foil, or we can also use a copper pipe. For the center electrode, right? So we start with this commercially available copper rod, copper wire. And then we can just further modify the surface with copper oxide nanowires. So it's a very straightforward one-step synthesis process. We just heat it up in the controlled environment with oxygen or just air, and then you can grow copper oxide nanowires on top of the center electrode. So this is the assay image showing how it looks like. So the diameter of the center electrode is about 100 micrometer. And then if you zoom in, you can see the copper oxide nanowires grow on the surface of this center copper wire electrode. So using these electrodes, we have demonstrated basically very good performance. So for example, with a reasonable flow rate of 1 milliliter per minute, we can easily achieve more than 6 log removal with a very small voltage, like just 1 volt. So the dashed line here already indicates that we don't have any live bacteria detected in the effluent. So we also have tried the system with different bacteria, gram positive, gram negative. We also dose the real river water with E. coli as a model bacteria. They both show very good performance. We also have tried to scale up the process a little bit. So this is a prototype in our lab as well. So it's about 2 meters long. And then basically you can expect that the flow rate can also be increased proportionally with a very high inactivation efficiency. So I really believe this is a new technology, and I really believe it can be very transformative for the whole water treatment industry, especially the water disinfection industry. So in the past few years, we have really focused on pushing this technology forward. So we have been working on the fundamental side of this study, trying to understand the mechanism of this electric field treatment process using a lab-on-a-chip devices. We also have been really addressed the challenges of the electrode development. So because the electrode is really a critical part of this technology. We also have combined this technology with like traditional disinfection processes like copper and ozone. And we also have developed test different power source for this technology. So in the next few slides, I will just briefly cover some kind of progress on each of these categories. So first, let's look into the electrode development. As I mentioned, the nanowire modified electrode is really the core of this technology to make it really work to realize the very low voltage applied but strong electric field in the system. But the insufficient stability of the nanowire is really one of the kind of bottleneck of technology. So this is the result showing that the removal efficiency of the system really declined after about 10 minutes of operation. And then we can also see that in the effluent, we can detect about 1 milligram per liter of copper in the effluent. This is already very close to the US EPA's standard for copper. And then if you look at the basically the mechanism behind is basically the electrode is not very stable. So that because of either electrochemical corrosion or a hydraulic scoring because the water is flowing. And then basically we are losing this copper and copper oxide nanowires in the system. So if you look at the surface of the electrode, and then this is the images, SEM images showing the situation after about 10 minutes operation, about the 2 hours operation. You can see basically after 2 hours, pretty much all the nanowires are gone. So we've been trying 2 strategies to improve the stability or robustness of the electrode. The first strategy, basically, we just replace the material, right? So with the more stable nanowire materials, for example, we replace copper oxide with copper phosphide, right? So copper phosphide is much more stable, it's much more conducting, also it's more electrochemically stable. And the second strategy, we just apply a protective coating layer on top of the on the surface. So for example, we have applied the polydopamine, the PDA coating layer. So basically a strategy that you want to just apply a very thin layer. You don't want to kind of block you don't want to cover the nanowire structures, but you want to have a layer that's really protective, and then you cover the surface with a uniform coating. We actually have combined these two strategies, so we end up with PDA-coated copper phosphide nanowire copper electrode. So here shows some more characterization results. So as you can see, the nanowire diameter is about a couple hundred nanometer, and then the coating, polydopamine coating on the surface is only about 50 nanometer. So we can control the thickness of this coating layer in a nanometer resolution, and then we optimize the coating layer to be eventually 50 nanometer, provide us the best performance. Basically, it's a trade-off of performance and then robustness, right? So if the coating layer is too thick, definitely they will affect the electric field distribution, and they will affect your performance. So eventually, this is the best result we have received so far. So with applied voltage of 1 volt, we have demonstrate the continuous high efficiency inactivation more than 6 logs for about 15 days. With this system, we also monitor the copper release in the effluent. So it's already less than 5 microgram per liter. So this is much lower than the drinking water standard. And also this is a really good indication that the electrode is very stable in the system. So with this electrode design, we believe is already good enough for some small scale applications, right? Point of use, small scale applications or emergency applications. But for large scale, long-term application, definitely this is still not good enough. So we're still on the way trying to make even better, even stable electrodes. Also, as I mentioned, we have combined this LEEFT technology with conventional water disinfection processes. For example, we combine it with ozone treatment. So basically, the idea behind is that in this case, we don't apply a very strong LEEFT. So, for example, it can be lower voltage, but basically we can increase. The LEEFT process won't be able to kill the microorganisms directly, but it will weaken the cell membrane, so make the cell membrane much more permeable for other disinfectants. So in this case, we can use about 50% of the ozone dosage comparing to normal dosage and realize similar disinfection results. In another example, we combine it with copper. So in this design, we actually don't even need to modify the center rod with the nanowires. We just use basically one level of electric field enhancement. So in this case, so conventionally, we usually we need to apply a 2 milligram per liter of copper or even higher to achieve really good enough inactivation for water treatment. This is already higher than the US EPA's standard for copper. But in this case, when we combine LEEFT with copper, we have realized that using only about 200 microgram per liter of copper, we can realize close to 6 log removal. So this is a very important results we have been pushing through. As also I mentioned, in this case, we don't even need to have the kind of insufficient insufficient stable copper electrodes at the center to realize the long-term application. So, and so far we have been working on all these devices. We have demonstrated very good performance. But again, all these devices is more like we know that the nanowire modification can be very important to really allow us to achieve very high performance with a small voltage. But we are still not sure how these bacteria are really how they are inactivated. What's the real mechanism? You see, the electroporation is a primary mechanism there. So this is more like a black box. We know bacteria flow into the system and flowing out, they are inactivated. But we really want to open the box to see what is really going on. We want to understand the mechanism more clearly. So that's why we have been using these kind of lab-on-the-chip devices to try to look at the mechanism a little bit more clear. So here are some examples of the chip design. So basically, these are glass chips. So we pattern gold electrodes on a piece of glass slide with photolithography and other relevant technologies. And then, for example, this is a typical design of the electrode patterns on this glass slide. And then here we have a positive electrode, negative electrode on the top and the bottom. And then we pattern the nanowire structures with this diameter, with this kind of geometry is about like about 8 to 10 micrometer, and the top is 200 nanometer, and the bottom is about one micrometer. So basically, we're trying to simulate the tip structures in the LEEFT systems. So this is a two-dimensional for just mechanism study, not for like real device, but really rely on this. We can realize the operational observation. Basically, we put this device under the microscope. We can do the LEEFT, and at the same time, we can really use the microscope to observe what is really going on. So this is a simulation of the results to demonstrate that theoretically, based on the values provided, we can really achieve very strong electric field near the tips, and then to about 20 kilovolt per centimeter, which is good enough to trigger electroporation, which should be able to kill microorganisms. And then basically what we do next, we use the Staphylococcus, which is a round-shaped bacteria, and then we just immobilize Staphylococcus on top of the chip, so provide us a very uniform coating layer on there, so we can really, so they are immobilized, so which should allow us to really monitor and observe this process very clearly. Okay, so here this is the chip before the LEEFT treatment, right? So there's a Staphylococcus laying there. And then so here shows basically the short video showing the real-time LEEFT treatment process. Okay, so let me play the video very soon, and then please pay attention to the areas with these kind of white lines, because these white lines indicates the location of the nanowires. And then theoretically, basically during the treatment, and then pay attention to the tips of these white lines, and then theoretically the bacteria located on these locations will be light up with reflorescence, which indicates the inactivation. Okay, so we have the PI dye in the solution. So when the bacteria is inactivated, the PI dye will diffuse into the cell, and then it will show a reflorescence color. So let me play the video. Okay, so yeah, so the time here, T0 means the electric field treatment starts, and then you can see at the basically the tip of these wet lines, you will see basically the cells being light up. There's some kind of a noise cells in the system in the background because they are already dead at the beginning. But if we do some basically results processing, this is results after the LEEFT. So basically, we remove the noise cells. You can see basically this LEEFT process only kill microorganisms cells at the tips of these nanostructures, right? So pretty much all other areas where you don't have the strong electric field, they are still fine. So only killed when the electric field strength is high enough. So with this platform, we have actually studied different topics on this kind of LEEFT technology. Which already really improve our understanding on this technology. Here, because of limited time, I will just show you two kind of most interesting findings in the past few years. So first one is that we noticed that this bacterial inactivation or microbial inactivation process by LEEFT can be super fast. Okay, so here shows the curve. The x-axis is the time, y-axis the relative PI intensity, or basically the redness. So how strong the reflorescence is. So you can see that all these lines indicate individual cells. So the red lines indicates the cell on the positive electrode, and the blue line indicates the cells at the negative electrode. And then you can see basically once we start the electric field treatment, and then it takes some cells takes a couple seconds to be inactivated, to be kind of fully stained with reflorescence, and some cells it only happens in even less than a second or a few milliseconds, right? So this is a really very fast inactivation process. And then also, as I pointed out here, this is the images showing how the reflorescence stain the cells. Right, so this is another cell showing that it's only like just a couple hundred milliseconds. And then also, as I emphasize here, so the treatment process for this curve is only one single pass of electric field with 20 nanosecond duration. Okay, so basically we just treat. It's not, you don't treat the cells, or you don't apply the electric field treatment for during all this kind of observation time. We only apply a single pass, which is only 20 nanoseconds, which should be considered a treatment time. It's only 20 nanoseconds, and then just take some time for for the fluorescence dye to diffuse into the cells. So that's kind of limited by how how big the damage is, and then that will determine how fast the diffusion can be. But the treatment time here only 20 nanoseconds. So this is a super fast treatment process. The second observation here is basically, as I mentioned before, this is an electric field treatment process. So this is not the electrochemical process. Okay, so if it's electric field treatment process, so theoretically, these nanowells, they don't have to have the direct contact with the positive and negative electrode. So for example, as I demonstrate here, these nanowells can just lay between the positive and negative electrode. So in this case, we can have a positive electrode at the top, not connected, and a negative electrode at the bottom. And then these nanowells just place in between. Okay, so because the electric field can be propagated through this space, so all these cells, as long as they located near the tips of these nanostructures, they can also be inactivated, right? So basically, with this kind of phenomenon, with this mechanism, we can also we actually have been testing these new applications, developing this kind of antimicrobial surface application with this nanowell array, right? So this is a kind of a comparison between the area you have this nanowell arrays, but the other is just a flat surface. You can achieve very specific kind of a high antimicrobial surface with the nanowell array. That means also we can precisely control the locations where we want the microorganisms to be inactivated, right? So that's why we can design this kind of specific pattern to demonstrate that capability. Okay, so with that, I just want to conclude my talk. So basically, I want to reiterate that the basic LEEFT technology, I believe, is a very new and transformative technology. So theoretically, we believe it can apply at really different scales, from point of use to kind of large scale, community scale water disinfection, or even large scale municipal water treatment. So it really depends on how you apply it. You can also combine it with conventional, water disinfection processes to reduce the chemical dosage. So here I just summarized the potential advantages of the LEEFT to conclude the talk. So the reason I put potential is because some advantages is we can derive it from the theoretical mechanisms, but we're still on the way trying to demonstrate it. So these are the things we already demonstrated. It has shown very high inactivation efficiency, very fast process. And then theoretically, the capital cost or operational cost can be very low because the energy consumption here can be super low because it's not electrochemical process. You rely on the current, but here we rely on the electric field. So theoretically, we want to minimize the current. So and then the energy consumption theoretically can be very low. One of the biggest advantage or basically from the mechanism, from the intrinsic mechanism of this electric field treatment is that theoretically this process has no any impact on the property of the treated water. And then most importantly, there shouldn't be any disinfection byproducts, right? So this process can be considered as an electrophysical process. We just broke the cell membrane without changing any chemical property of the water to get microorganisms inactivated. And then other advantages can also include you can basically operate solely on electricity. There's no over treatment. You can just, it doesn't matter if you treat it too much. And then it's very easy to operate and then very safe to the operators in the nearby community. So in the end, I just want to thank all my students, postdocs who have been contributing to this project and also my funding agency. With that, I want to thank you all for your attention. I'm happy to answer any questions if you have.
Okay, thank you very much, Xing, for a very wonderful presentation, and also Professor Liu. So we have some questions. You may also see that in the question box, but it's probably the audience may not be able to see. So maybe I'll just read some questions. Basically, some people are asking both of you about the scale up of the processes. So any idea on how to scale up? Have you thought about that? And also when you come to the scale up and real application, water chemistry from the mother nature coming, such as you have some TDS in the water, and what these TDS affect the operation. Maybe Professor Liu first.
Okay.
About the
Thanks for
scale up. Yeah.
Yeah, the scale up is the key point for our research, and we are working on this part for several years. Frankly speaking, it's really hard and also very challenging. So we all found that once the membrane was scaled up, but the applied electric field cannot evenly distribute it from just throughout the membrane matrix. So right now we just use some simulation like CFD simulation to simulate how to this distribute this like flow field, electric field. And also for the scale up the membrane, we have some just attempts, and we also get some examples and also apply the upscaled materials for some pilot scale applications in wastewater treatment plants in Dalian City. And we just follow the conventional method for preparing the hollow fiber membranes, but we modified the ink to make the product membrane conductive,
Mhm.
and just try to keep optimizing the ink, and just keep trying for I think
Sure.
for 3-4 years. Right now we can get a better one, I think.
Mhm. Okay, very good. Professor Xie,
Okay, yeah,
about the
thank you.
scale up. Yeah.
Thank you for the question. Very good question. So for our LEEFT technology, I would say the mechanism itself is very, very scalable, right? So it's just electric field treatment. But the current challenge for scalability is really on the nano, modified electrode. So basically, the fabrication process is still not like, very scalable. And also, when you try to make large scale devices, you probably don't want to use it in a very short time, right? So the robustness, the durability of electrode is very important. Even though we can make large scale electrodes, you want to use it for a long time, right? So that's really the limit there. And then also that's one direction we are pushing. So, but we also, as I mentioned, we also try to combine the LEEFT technology with more conventional processes, right? Conventional disinfection, disinfectants like a copper. So basically, we believe for that direction, for this combination, is already very scalable. So we actually have received some more like funds on commercialization. We're actually building this kind of scale up process, scale up process. So that's hopefully we will be able to demonstrate some results by the end of this year. So that's a goal that we're trying to. So for the devices in the bench scale device is just a few milliliter per minute. We're trying to achieve maybe at least 100 times larger flow rate by the end of this year. I also see questions from the Q&A. Do you want me to just take that?
Yeah, please go ahead, please. Yeah.
Okay. So first one is about the IOS. That's also a very good question. So definitely, when you apply electricity, you will apply a voltage across the electrodes. You will see the current, right? So when you see a current, most likely there's some electrochemical reactions, and most likely will be probably some IOS generated. So whether you have IOS generation really depends on the condition you apply. So in one paper, ESNT paper published last year, we really try to control the different electrochemical conditions to see under what conditions you have IOS and under what conditions you don't have. So there are different ways to differentiate that. But definitely in our early stage devices, especially when we apply DC or small, even though it's a low voltage, we believe there's still contribution from the IOS generation. That's why as I mentioned, it's very difficult to tell if you just look at a device. The cell flows in, flows out. It must be a combination of different mechanisms. That's why we try to understand the process on the chip, so where we can really observe what's really going on, and you can differentiate the different contribution of different mechanisms. Okay, so I think next question is also
Yeah, the next question is about the disinfection contribution or to the
biological
biological
stability
stability.
of
Yeah,
water.
yeah.
That's biomass from subsoil growth. Okay, so again, this is also a very good question. The process, if it's pure electric field treatment, if it's pure electroporation, theoretically, as I mentioned, you will not change any chemical property of the water. So the cell will just the cell membrane will be ruptured, but all the cell components will still be there. So the cells will be inactivated, but they can probably become the biomass for other bacteria or for other bacteria to use. But again, so in the real applications, depends on purpose. Theoretically, you can also intentionally introduce some electrochemical reaction. You can be at least especially these electrochemical reactions happens also near the region of the electrodes. Theoretically, we can try to combine the electric field treatment process with electrochemical process if you want to also get rid of all the chemicals or realize some kind of electrochemical oxidation. That's possible. But for the electric field treatment process itself, theoretically, if you control it very well, it doesn't change the physical chemical property of the water.
Let me continue these questions. When you say if you can control the process really well, then my immediate question is that how will you control the process? What is the objective parameters that you can control? Is that like oxidant levels? Is that like because if you want to measure the bacterial or even other biomass concentration, it will be very difficult. So what is the target parameter for you to control?
We have to primarily rely on controlling the electric conditions. Basically, that's the voltage, the positive. So usually you won't be able to apply just DC, right? So you have to use pulses. You can use symmetric pulses, which you have a positive and negative amplitude the same, or you can have a different amplitude, or you can control the pathways, right? So that's a very important parameter. So for example, if the pathways for DC voltage, if it's based on our findings, as long as if it's longer than let's say 10 microseconds or 100 microseconds, you will introduce electrochemical reaction. Even though it's very small amount, you probably won't be able to detect it in the bulk solution, in the bulk effluent, but actually you are generating very small amount near the surface of electrode, right? So that's why we have to, if you want to really control it very well, you have to control a very short process. And also the duty cycle, basically you turn it on and then you can let the system to basically relax for a certain period of time and before you put another pulse. So that's a way to control it.
Yeah, please. And then the following questions about the desalinations. Yeah.
Short answer is no. As I mentioned, it doesn't change if you just relies on the electric field treatment, it doesn't change the physical chemical properties of water. So you won't be able to do deionization.
No, I think the background for this question is that if you want to run the desalination, one of the issue in the desalination is to try to remove biomass, which can cause the biofoulings. So so you don't touch the removing the salt part, but rather how about controlling the biomass?
Yeah, so definitely this technology can be used for antimicrobial applications, right? So if it's for biofouling control, I think some people actually are working on that. We're also doing this similar application in terms of antimicrobial surface, but not necessary for desalination applications. But yeah, again, so.
Okay. And the next question is about the turbidity. So he was asking about whether it's suitable for 100% transparent of the water, or if the water is very milky, lot of particle inside, does it work?
So as I demonstrated in my slides, so it depends on how the electric field strength distributed, right? Theoretically, we're trying to locally enhance the electric field. So that means those microorganisms has to transport to these regions. So the turbidity itself, basically that means that these cells, they need to have the chance to go to these regions. So the turbidity doesn't affect the electric field distribution. But if you have too many particles, too many stuffs or organic matters that are attached to those particles, that may kind of push them over for that can basically be an obstacle for them to move towards these regions. That would be a issue there. But in terms of transparency comparing to the electromagnetic waves like UV light, electric field treatment, electric field itself, it doesn't matter if you have the higher capability.
Sure. Then another question is how do you monitor the concentrations that have been administrated at the time, unless other disinfection system where you're able to determine the residual chlorine level? Similar to the question I was asking. Yeah.
Right. So this is we should consider this is a physical treatment process, right? So after the treatment, there's nothing residual. Okay. So that's why also it doesn't matter if you over treat it. So if the electric field strength is strong, it doesn't matter, right? So we have to depends on your target. It depends. We have to pre-assign some kind of conditions to the system, right? So we won't be able to tell how strong it is based on the measurement from the
Sure.
effort.
All right. I think we all run out of time, maybe just a few minutes. So the other question probably can be addressed by Professor Liu. So one guy was asking the duration of the membrane nano filters. So can the filter be used for a long time, or just like few months? Yeah.
That's a good question. Also very important. Right now we have tried the long term about 6 months usage. The membrane is still working very well, and we didn't try that longer.
Okay. Then another question is that do you see any nanoparticle that being dissolved in the water, or they are staying in the treated water, and such would these have any impact on humans? You use a
This
filter, particle
yeah
coming out.
This may happen once we apply very high voltage, such as maybe 4 to 5 volt, to oxidize this carbon. Then they will release some carbon materials. But right now, we don't need to exert that high voltage, and also mostly we give some negative charge on the membrane, so it only repels some pollutants rather than to oxidize some molecules. For the industrial or pilot scale application, we only give the negative charge on the membrane to repel only. We don't need to hope to give some oxidation.
I think probably this will be the last questions. Somebody was asking whether the nano material that you develop can be used for treatment of uranium contaminated water. Uranium.
Yeah, we tried before, maybe 2 or 3 years ago. I also have a paper published on that part. We give some nitrite, the sodium chloride as electrolyte, and to convert urine into some like a nitrogen. I think.
Okay. I think probably we finished all the questions. So look like no more questions. Yeah. So thank you very much for both of you for giving such wonderful presentation. In particular, Professor Liu right now is 12 o'clock in the midnight, and you are still feel energetic. So thank you very much. I really appreciate. And Dr. Xie probably is a midday, so you have to go and do more of your work. Very interesting, very nice to listen and learn all this new knowledge from you. The last small thing that I would like to remind you is that the audience, that we have a few conferences coming and also webinar. So this is the first one. All right, and then we have a few others. Okay, so there is a Water and Development Congress exhibition, which will be not so far away from China, Thailand, but will be almost a yes from now. All right. So if you have time, a resource, please join. And then another one. Okay, the last one is very important to the new member, in particular the student member. Good news for you. We got 20% discount for the new member. So please do join IWA as a member. All right. Thank you so much and have a good day or good evening. Bye bye to everybody.